Welcome to The Explainer. Today, we're diving into the spectacularly dramatic life story and aging process of a star. We are going to unpack exactly how and why a star undergoes a massive, mind-bending transformation known as the red giant phase. Okay, let's dive into this. Think of a star like a long burning fire. That is absolutely the perfect mental model for us to use today. You see, stars aren't just these fixed, unchanging little lights in the sky. They're incredibly dynamic engines that evolve over vast timescales. Think about a campfire. It burns super bright for a while, but eventually it starts running out of wood, right? It swells, it shifts color, and it behaves completely differently as it struggles to stay alive. Well, a star goes through its own life and death struggle just like that, undergoing a profound transformation that literally takes millions or even billions of years to unfold. Part 1. The stable years. So, to truly appreciate how drastically a star changes, we first need to establish what a normal star looks like before things start to go wrong. Most stars spend the vast majority of their lives in a remarkably steady, reliable period. We call this the main sequence stage. And right now, our very own sun is sitting comfortably right in this exact phase. Deep down inside its core, it's continuously smashing together hydrogen to make helium through nuclear fusion. This fusion is the star's engine. It pumps out unfathomable amounts of energy, and that energy is exactly what makes the star shine so brightly. Now, during these stable years, there's this incredibly delicate physical balance at play. It's essentially a giant cosmic tug of war. On one side, you've got the crushing, immense force of gravity, constantly trying to pull all the star's mass inward, literally trying to collapse it. But on the other side, you've got the incredible outward pressure from that fusion energy we just talked about, pushing back just as hard. So the key takeaway here is that as long as the star has plenty of hydrogen fuel, these two opposing forces are perfectly matched. The balance holds, and the star stays completely steady in both its size and its brightness. Part 2. Running out of fuel. But, nothing lasts forever, not even in the cosmos. After millions or billions of years of perfect, peaceful balance, that core hydrogen eventually begins to run low. And when that happens, well, all hell breaks loose. Let's walk through this rapid, violent chain reaction. First, the hydrogen runs out. Because fusion slows down, that crucial outward pressure suddenly drops. This leads directly to step 2. Gravity finally starts winning the tug of war, causing the core to rapidly contract. Step 3, as all that matter gets squeezed tighter and tighter, the temperature and pressure inside the core spike to just unimaginable levels. And finally, step 4. In response to this intense internal squeezing, the outer layers of the star do the exact opposite. They dramatically expand outward. The delicate balance is officially broken. Part 3, the red giant phase. And that massive outward expansion, that triggers a total identity crisis for the star. The physics here are actually pretty counterintuitive. As those outer layers expand, they spread out over a vastly larger volume of space. Now, because that surface area is suddenly so much bigger, the surface actually cools down. It's a crazy paradox. Even though the star is technically releasing more total energy than it was during its stable years, it's spread so incredibly thin that the outer skin gets cooler. And in the universe, temperature dictates color. Hot stars are white or blue, but cooler surfaces, they glow reddish. And that is exactly why they earn the name red giants. Now, I really want to emphasize something here. The giant part of red giant is completely literal. We aren't just talking about a minor swelling. It is enormous. When a star like our sun eventually hits this phase, it'll grow so unbelievably large that its outer boundary will stretch deep into our solar system. It will swell so much that it's going to literally swallow the inner planets. It could completely engulf Mercury and Venus too. It's a terrifying but totally awe-inspiring scale when you really stop to think about it. But we do need to clarify what this planet-swallowing monster actually looks and feels like. Despite being so massive, the red giant is actually extremely diffuse on the outside. This means those expanded outer layers are way less dense than the star used to be. Yes, it's grown to monstrous proportions, but that outer shell is surprisingly thin, just kind of hovering out there in the vast emptiness of space. Part 4. Inside the swollen star. So we know what's happening on the massive, glowing red outside, right? But the story is far from over. If we peer deep back into the heart of the star, we find this incredibly dramatic paradox. While the outer layers are drifting out, cooling down, and turning red, the inner core is fiercely battling against gravity. It's doing the exact opposite. It's contracting, it's heating up intensely, and it's desperately trying to start entirely new fusion processes. It is literally a star divided against itself, being ripped in two wildly different physical directions at exactly the same time. And what this tells us is that a red giant isn't just some bloated, dying zombie star. It is highly active. It's furiously fighting to stay alive. Hydrogen fusion might have completely stopped right in the dead center, but hydrogen can actually keep fusing in a shell wrapping around the core. Meanwhile, the shrinking core itself hits such extreme temperatures that it actually unlocks a brand new power source. It literally forces helium to start fusing into heavier elements like carbon. The star is basically inventing new nuclear reactions on the fly just to stave off total collapse. Part 5. A beautiful demise. But a star just can't sustain this frantic, unstable giant phase forever. Ultimately, this entire journey breaks down into 3 distinct eras. First, you have billions of years of perfect balance in the stable main sequence. Then, the fuel runs low and we enter this turbulent, desperate red giant phase for a few million years. And finally, this erratic chapter gives way to a surprisingly peaceful end, where the star simply lets go and sheds its expanded outer layers out into deep space. And what exactly happens to those outer layers? They transform into what astronomers call a planetary nebula. And let me tell you, these are absolutely stunning. They're some of the most beautiful, intricate structures in the entire galaxy. The star essentially just exhales, gently blowing all that diffuse material back into the cosmos. It's an incredible visual legacy. It returns all those heavy elements it forged over billions of years back into the universe, seeding the galaxy to potentially form new stars and maybe even new planets way down the line. But what about the core itself? After all those outer layers drift away, all that remains of a once mighty star like our sun is a white dwarf. Think all the way back to our campfire metaphor from the beginning. If the red giant was the swelling, struggling flame running out of wood, the white dwarf is the final glowing ember. It's incredibly dense, it's incredibly hot at first, but there's no more fuel to burn. It's just a remnant core, sitting alone in the dark, slowly, and I mean slowly, cooling down over billions of years. So, after taking this crazy journey from a perfectly stable fire to a swollen planet-eating giant, all the way down to a tiny, glowing ember, I want to leave you with this thought. When you look up at the stars tonight, knowing what you know now, how many of those tiny pinpricks of light are steady, perfectly balanced fires? And how many are actually enormous red giants swelling up and fighting their dramatic final struggle against gravity? The night sky isn't just a static painting, guys. It's a canopy of living, breathing, beautifully complex stories. Thanks for exploring this with me today. Keep looking up and keep asking questions.